Hello, this is Argan Kukitaev, and I am walking you through the steps of the calculating portfolio value at risk using Copulas. In the previous step, we calculated, or at least we looked at how to calculate P&L P&L distribution one day forward, right? So again, the idea is that since you have, since our data set was daily returns, historical data set of daily returns, we fit the copula and marginals, we obtain joint distribution of daily returns. Now, using this joint distribution of daily returns, we were able to produce the scenarios, whichever number was requested, let's say 100,000. So under these 100,000 scenarios, under each one of these scenarios, we should be able to calculate whether we're gaining profit or losses of our portfolio on a given day, right? So we start, let's say, in March 11, whatever the date I'm asking you in the assignment. And then for the next day, project your portfolio value, calculate P&L, we get the P&L realization for each scenario. So if you have 100,000 scenarios, you have 100,000 different P&Ls. So that's was the step number. Well, it was function number 7. I don't remember which step exactly it is, right? I'm giving you just 1 point because it's very easy. It's one line of code. Once you got the P&L, right, we can now, once you got the P&L, you pretty much are done in terms of the value at risk, right? Because value at risk is nothing more than what? It's nothing more than quantile. So let's see where we are. Right, so once we got the P&L here, we call this function number 7, which we implemented. Now, where is the value at risk? Am I calculating it here? Probably not, right? I'm calculating it somewhere lower, right? So it's a percentile, right? So once you have P&L, all you need to do is to get a percentile to calculate VaR. I'm calculating VaR for you. It's like it's too easy, right? So we got that, but we don't know how good is this number, right? So having the P&L is a great thing. Well, this distribution doesn't look very interesting. Right. Oh, because it's an assignment. It's not my example file, right? It's kind of dumb. So I'll show you the P&L how it looks like in my example. Actually, it's more interesting, right? So if you ran my example, and I'm not sharing this with you, then you would have gotten something like that. So if you did your job correctly, you should get something like this, right? And we can see these plots. Let's see them in my example output. They are in P&L summary, right? So if you did your job right, then your plot should look something like this, except here again it's different data, different numbers, different holdings, so please do not try to reproduce these plots, but they have this sort of a look, right, these plots. So let's get back here. So you don't have to calculate VaR, right? I calculate for you, but you have to produce me the P&L sampling from P&L. Now we need to assess its quality. How good is our VaR? And this part consists of 2 steps. The first step is the following. We just need to first of all see whether value at risk number is converging to any kind of number, because when you have Monte Carlo, every simulation brings you different numbers, so you run a lot of simulations and get some hopefully good number, right? So you will be producing a graph like this. So a graph like this shows how the number value at risk is changing with the number of simulations. So in this case, for example, I used only 10,000 simulations. So I'm producing this graph, and you see it's very jumpy in the beginning, but towards the end it seems to be converging to something. So it's less jumpy, right? It's not moving by as much, it seems. But we have to study this. Is it really going on, or it's just visual trick, right? So that's what this part does. The part study convergence of Monte Carlo. So the way we do it, we're using this test based on binomial distribution, and in this part of our work we will use binomial distribution twice, but in a different way, differently. So it's a binomial distribution, but it's used differently in two parts, in this part which we are discussing now and in the next. So in the convergence part, what we're looking at is the following. Where is our convergence, right? So we will have to apply function 8, right? So binomial distribution, and you will have to implement it in function 8. So here, again, I give you all the code which supports it, but you have to implement this function 8, which is let's see, MCCI, right? So what it does is the following. It gives us the confidence interval. So we're going to use this binomial distribution to produce confidence intervals over quantile, because as I said, value at risk is nothing more than a quantile of your distribution. So since we got the sample from distribution, let's say 100,000 simulations of our PNL, now using this technique based on binomial distribution, we should be able to produce confidence interval. So you will have to produce confidence interval lower and confidence interval upper. And then we're going to look at the difference between them and compare it to some number. So what we're going to do in this assignment is we're going to say whether confidence interval is narrow enough, right? So we'll see it later. But basically, once you have confidence interval, we can see whether it's narrow enough, whether your number is converging. So the technique, function 8, right? So here, let's see. Was it function 8? Oh, actually it was function 9. So why don't I will fix this, right? Because it was, I had this as function 8. So the confidence interval is function number 9. Should I have just replaced them? I'll leave it there. Who cares, right? The order doesn't matter. So you'll implement this function. All you need to do is to provide PNL and the percentile. In this case, let's say if you were using 75th percentile, you would provide 75 here, and the PNL variable is just your PNLs under each scenario. And having these two quantities, one array and one number, you should be able to produce confidence interval. Again, we will cover this during the class, right? So for this, you're getting 2 points. There's a little work here, so I'm giving you 2 points. Then, well, so now we know that our VaR, right, in this case, right? So let's look at confidence intervals. So for instance, we produced our value at risk, and it was $573 loss, right? We could have 573 or more loss in 25% of the time, every fourth day, right? And we are saying this number 573 is with this confidence interval, lower and upper. It's -1 sigma and +1 sigma. Right, so then we will look at the difference between them. If the difference is small enough compared to VaR itself, maybe, right, then we will say, well, it's good. So in this case, we see that again, this confidence interval is narrowing, but is it narrow enough, right? So 658, 518. So let's see, where's 658? It's somewhere here, right, on the plot, and 518 here. So it's a very, very wide confidence interval. So I doubt that this converged yet. So 10,000 is probably not enough. We should let it run more. And in your assignment, you'll run it more, let's say 100,000 or whatever, and maybe at that point it will converge. So here it should not say it's converging. I mean, it's converging, but it didn't converge yet. So the outcome of this assessment should be no, it didn't converge, let it run a little longer, right? I think that should be the assessment. The next then is the following. Okay, we got this VaR number, and we figured that it's stable, right? Monte Carlo itself, it converged to this number. Great, so we got this number. Monte Carlo itself seems to be working. But does the whole process which we went through, does the process as a whole work? And that we are going to test with something called coverage test, and for each you're going to get 2 points. And coverage test again uses binomial distribution, but in a different way. So we will learn how to apply it in the class. So it's a test of the value at risk. In a nutshell, I could say value at risk tells you, so if your value at risk was 573, it will tell you every fourth day your loss will be more than 573. So this coverage test we're going to implement literally tests that. It will actually go into the test data set. Remember I said we divided the data into train and test data set. So we trained the model on train. Now we're going to get the test data set and see whether the loss on every day of the test data set compared to our portfolio value is more than 573 times, and how many times. So approximately in a test data set we should see 25% of the time the loss is greater than 573, right? Because it's a 75 percentile loss. So it's almost like a literal comparison. And that's what we will do in a coverage test. And that is turned out to be function number 8, right? So coverage test. So there's a bunch of parameters you have to produce, and in the output you will have a p-value of this test and plus the number of breaches. So let's actually take a look at the output of this test. It will go into the report, right? So into the report, are we yeah, look at this. So I believe this is the p-value. VaR coverage test. Right, so I think in the code itself, somewhere here, you will be printing the number of okay, confidence interval is here. Oh, here, coverage test, right? So look, we have 86 days in training data set. Remember, we had 166 in training, and then 86 in test, sorry, data set. So in 86 test data set, we see that VaR breaches, there was just one VaR breach. And exceedance ratio is like this, right? So this is not a good fit at all. This value at risk did not run very well here, at least in this implementation. Oh, because this is an assignment, right? Let's see our example. Did it work in the example? Coverage test. Okay, looks much better, right? So we had 87 test days, and we had 28 breaches, which gets to exceedance ratio, which means the number of breaches compared to the number of days was 32%. But remember, our Monte Carlo, sorry, our value at risk in this example assignment was 75%. So we were expecting 25, but we got 32. So it's not the same number, right? But how close is this? So we are going to use binomial distribution approach to calculate this coverage test, the success or failure, and you will have to implement it again in function number 8. So that was your test VaR coverage, for which you get 2 points. So if you add up all the points in this assignment, you'll get 20 points. Now the final result is here, right? So we have this final result section of the code. You don't have to touch it really. It runs it all for you, but it will summarize all these tests and all the work you've done into this final report sheet, worksheet, right? So you will get all these numbers here, so you can analyze them by just looking at the code. Take a look at the code and you will understand how this works. But this is the main place where I'm looking at when I'm grading your work, right? So I'll start with the sheet, and then I'll go and look at other stuff. I'll look at your write-up and so on. So this sheet is very important. It's very important that you keep this format. And on that, we're done. Good luck with an assignment. Bye.